In this example, we're going to consider some operations in Mathematica that are good for manipulating clouds of points of data. Um, and what do I mean by a cloud of data? Well, imagine that you've made a bunch of different measurements of the position of something and you haven't always quite gotten the same answer. So here's the position and you've gotten a variety of values that look something like that. There's a cloud. You can imagine this being in 3 dimensions or in more dimensions, and so you might want to know, well, how well do I know this position? How wide is my cloud? Of course, if your cloud were round and had the same width in any direction, that would be an easy question to answer, but maybe your cloud is a little bit less well known in that direction than it is in this direction. And if there were a third dimension, it might have different width in that way. And implicitly what I'm saying is that the cloud is somehow looking like an ellipsoid and has principal axes. And so how do you go about finding those? How do you go about describing this cloud of values around some mean in terms of the mean and the widths in these different directions? How do you do that? That's what we're going to talk about in this example. So of course the mean, the center of the cloud, is a relatively easy thing to define. If you've got a big long list of these data point values r sub I, well then the average of those is going to be your best guess about where the center of the cloud is. And then you can consider the deviation of all of the points from that center. That's basically just taking this point here, defined as the center, to be the origin. And then how do you go about describing the width of the cloud? Well, it turns out to be a good idea to construct the following object, a matrix which is something like sum over the different particles of the alphath component of the deviation of the ith particle times the betath component. In other words, alpha and beta are, x are chosen from among x, y, and z. So it could be the case, for example, that this cloud was actually oriented along, the x, y, z axes, but the cloud actually, pointed along z, for example, and had a width in x and y. And then these would be the variances, the spreads of, if I divide this by 1 over n, would be the average spread of the values around this origin here in the different directions. It will turn out in general, of course, that the cloud doesn't point along any particular predefined set of axes, and then you might like to know, where are these axes? It has 3 axes. Call them, say, E1, E2, and E3. And so how do we get those if we knew this matrix? Well, the answer to that is that these E's are that the E sub I, let's call them, where I is now 1, 2, or 3, are the eigenvectors of M. In other words, M dot E is some epsilon E, where epsilon is a number, namely the corresponding eigenvalue. And furthermore, the width in the direction E sub I, taking those to be unit vectors, which we can certainly make them be unit vectors just by scaling them, that the width in the direction e sub I is the square root of that corresponding epsilon I. Well, so the point is that Mathematica has the ability to compute eigenvectors and eigenvalues easily, given the numerical values of the matrix. So what we'll now turn to do is to show how we can take a cloud of points, find the mean, find this tensor here, which would be called the radius of gyration tensor, maybe called by other people the moment of inertia tensor. And then we'll compute the eigenvectors and eigenvalues, and along the way we'll actually draw this cloud and draw the axes and see that the axes do point as computed in the direction that our eye tells us that they should. So the first thing is to create a cloud to play with. And that we're going to do by effectively creating some fake data, you might say. So first we choose where we want the cloud to be. And I'm just making some arbitrary choice. So this is going to be the center of the cloud, and these are going to be the widths. You might say sigma x, sigma y, and sigma z. They're going to be the widths of this cloud, and again I'm just choosing these just arbitrarily. And then I'm going to generate a table of data which will be each entry in this is going to be an x and a y and a z, and they're all going to be taken as random reals with a Gaussian distribution about the corresponding mean value with the corresponding width that I just chose arbitrarily. So I want the x1 to be around x0 with width sx, I want the y to be around y0 with width sy, and I want the z to be around z0 with width sz, and let's make, I don't know, 10,000 of them. So then I want to plot those, and I want to plot them with some halfway reasonable choices of x min and x max ranges, which I could take to be x naught plus say 3 sigma either way, and corresponding for the y and the z. I find copying is sometimes easier than typing. And then we're going to list plot the data. Oh, but this is not just any old list plot. This is a list point plot 3D. It's a way of plotting in 3D just loose points. We'll take the plot range to be, as I've somewhat laboriously constructed here, and then I want the lengths of the sides of the box as they appear on the screen to be representative of the actual width of the cloud, not have the thing rescale it in some funny way. And so that I can see into the cloud, I'm going to take the opacity to the points to be, well, to make them slightly transparent. Alright, and there you go. So there's my cloud. You can kind of spin it around and look and see, look at it from different directions and see that it is what we expect. It's an ellipsoid shaped cloud because that's how we built it. Okay. So now we're going to rotate these points about their mean in some random way, just for fun, just so that we won't quite know anymore which way the cloud's supposed to point. And to do that, we need to construct a random unit vector around which to rotate. And that in itself is a useful little thing to be able to do. So to construct a random unit vector, a unit vector is a thing that lives on the unit sphere. And what we know how to do is to construct random reals that, using, for example, the function random real, which live on the interval 0 to 1. Now, that means we know how to construct things that sit inside a unit cube, or in fact we could make this be from -1 to 1. So we know how to make things that sit centered around the origin in the unit cube, but not a unit sphere. So the scheme for generating a random unit vector is you generate an x and a y and a z that live on the interval -1 to 1, and therefore in this cube. Sometimes they'll live inside the sphere, and sometimes they won't. So you keep trying until the triplet that you generate is inside the unit sphere. And then you rescale to make it a unit vector. And the reason you do that, if you just rescaled the very first thing that you got to a unit vector, you see you tend to generate more things that point toward the corner. By choosing only those vectors that live inside the unit sphere, you get something which is isotropic, which doesn't point any particular direction any more often than it points any other direction. And you've got to throw away some vectors to do that, but that's alright. You just keep trying until you get one that lives inside the sphere. And so then you rescale that to make it a unit vector, to put it from here, say, onto the sphere. Okay, and now you have a random unit vector. Alright. So the way that that works in Mathematica is to define a function called random unit. And as promised, first you, well, you'll see why my n is going to be my unit vector that I'm trying to generate. So I use a while loop to say while the norm of n is bigger than 1, keep trying. And the keep trying part is n being set to random real from -1 to 1, a list of 3 of those. Like that, and that closes the while loop, because the while loop will fail, that is, you'll fall through the while loop as soon as you get one of these things that has length that is 1 or less. So I just start the ball rolling by giving n any old definition which I know has a length which is too big, and so then the while loop will start working, and as soon as it finds an n which is shorter than that, then I'm done. And then what I want to return is n divided by its own norm. And that closes the module. So that thing there should give me random unit vectors, and I can check that by applying the norm to the answer. Okay, so that's how I get random unit vectors. That's a useful little thing to know. Now I want to construct a rotation matrix for a random rotation around a random vector. So we're going to call that random rotate. And we'll use Mathematica's built-in rotation matrix function, which rotates about, in one form, rotates about a vector by a given angle. And the way it works is, I think well, we can check this. There's several forms of this function. So theta w gives the 3D rotation matrix for counterclockwise rotation around the vector. Okay. So we'll choose randomly the rotation angle between 0 and 2 pi, and then we will take a random unit vector, and that will give us, oops, we meant for this to be a function. Right. That will give us a random rotation matrix. Then to rotate our cloud with respect to its center, first we make our random rotation matrix, and then we take our data to be, we need to apply to every triplet in there, first subtracting the mean and then rotating. That effectively rotates around the mean as the origin, and then adding the mean back. So here I am adding the mean back. Here I am applying the rotation matrix to the point minus the mean. And that's a function that I want to map onto every entry in the list called data. So I'll use that to prepare well, I'm just dumping it back into the old variable data. So it's actually going to clobber the old value. So I do that. And now let's just plot it again. We need to find the positions of the min and max box lengths over again. And that can be done in the following way. I'll explain this in a minute. So data is a list of triples. Transpose of data is the long list of x's, and then the long list of y's, and then the long list of z's. If I take min applied to that, then what I'm getting, or min mapped onto that with this thing here, then what I will get is the minimum of the x values, comma, the minimum of the y values, comma, the minimum of the z values, because each entry in the transpose thing, which is a list of three things, the list of the x's, list of the y's, list of the z's, I will take the min of, and then those will get stored in x min, y min, and z min. So like that, and like this. And those I'm going to use in doing the plot of the now rotated data using the same list point plot thing. Actually, I think I can just copy that right here, except I don't want to use the box ratios the way that they were before. I need them to be like so. Okay, so my cloud is now rotated some other totally off skew kind of direction. Fine. Now we want to go about finding the principal axes. Okay, so first we compute the mean position. This is our fake data, right? Randomly rotated and so forth. Of course, we know what the mean position is because we produced this, but now we're going to pretend we don't, and we just say the The average positions are the mean of the data. Okay. Now we're going to compute the radius of gyration matrix. And that's going to be, well, so it's a table of the alpha and beta components. So there's a table to be done, and then inside that there's a sum over the data with respect to the average position. I'll explain this after I get through typing it. Okay, so I and j here are the alpha and the beta of the m, and so this is the ith component of the kth data point, and then minus the average position. Actually, that should be minus the ith component of the average position. And then this is the same data point, but the jth component of it minus the jth component of the average position. Okay, and then that's summed over k, summed over all of the points in the data set. So that sum then is the ij entry of the radius of gyration matrix, and then we make a table of those, a two-dimensional table, okay, which will produce a matrix. And at the end we divide by the number of data points, because that was supposed to be done to every one of those sums. Okay. So there's the matrix written out. And now we need the eigenvectors and eigenvalues of that. Which are just easy as pie to get, given Mathematica's ability to compute eigenvectors and eigenvalues. And there they are. Now the standard deviation values are the square roots, as I mentioned, of the eigenvalues. And there they are. So here's the longest axis, the next longest, and then the shortest axis. And the corresponding eigenvalues are, corresponding eigenvectors are this one, and that one. See, the eigenvectors are a list of 3 vectors, right? The eigenvalues, that's this thing right there. So now we want to draw the principal axes using what we've just computed. So I'm going to draw lines going from the origin out plus or minus 2 standard deviations in each of the 3 directions, and I'm just going to call that principal axes. I use Graphics 3D to draw. I'm going to make a pretty choice for the thickness, or what turns out to be a pretty choice, and I'll choose different lengths, different colors for these different vectors, which are going to go always from the origin to the origin shifted by some amount. So there's the first of the standard deviation values. So there's an arrow that goes one direction along that axis, and here's the arrow that goes the other direction along that axis. And now I'm just going to copy that to do the second and third one, but I'll change their colors. And change these indices so that instead of the first width in first direction, I'm talking about the width in the second direction along the second, along the second direction, and along the third direction. Like so. And so that's a big long list of graphics primitives, which I will save like so. And then if I want to see them, I use show, and I'll show them along with the data plot. And whoops, something went wrong. Let's find out what it was. Must have typed something wrong. Oh, there's supposed to be a comma after that blue. Let's see if this fixes it. No? Oh, I forgot the word arrow somehow. Blue, comma, arrow. Let's try that. Okay, you can see the three different principal axes in there. It might help if I did the data plot with a little bit less opacity. So let's take this and turn it down. And now if I do, now it's a little bit easier to see. Yeah, okay. So you can see the three principal axes, and they point along the directions that they're supposed to point. Now, we might be interested in looking at this thing along one of these directions and projecting it, so that we look at the cloud along, sort of one of its two-dimensional projections along one of these vectors. So how could we do that? Okay, so I want to construct a set of the projected data, and the way I want to do that is by taking the components along two of the eigenvectors. And I want to just make things simple for myself and subtract the mean position while I'm doing it, so I'm only looking at the displacements. So essentially what I want is to map the point minus the average value dotted into one of the eigenvectors. Let's take the second one, and then the same point minus the center dotted into the other eigenvector. I'll take the third one, and then this constructs a pair, and that is now a function which I'm going to map onto every element of the data. And what that should produce is a list of pairs. So there's the first such pair. And then I can do a list plot of those. I'll find minimum and maximum of the projected data in the same way as I did before. And then I can do a list plot of the projected data with the plot range set using these min and max values. You don't have to do that, it's just convenient to know what the range of the data should be, and again set the aspect ratio to be what it should be, which is comparing the y and x ranges in the following way. And there you go. So now we're looking down the y-axis because we projected along the 2 and the 3 axes to see what's going on there. And we could do the same thing with the 1 and 3 axes and 2 and 3 axes. So that's the cloud as viewed along the long axis, along that direction, with the axes that we're looking at oriented with respect to the second and third eigenvalues. We can project the data onto a single axis as well. We can project the data along a single axis as well and take histograms. So just following the same scheme, but this time we only project along one direction. Let's say the long direction this time. And then we can, for example, make a histogram, as I say, of those deviations to see what the distribution looks like in more detail. And it looks approximately Gaussian, which is no surprise since that's how we built the thing in the first place. When you have a distribution like that, you can compute a lot of quantities about it. For example, the standard deviation, which is about 2, which, if you can remember way back, was about the value that I took for the standard deviation in the z direction. And there are other things that you can do in terms of manipulating the histogram at that point. But that gives you an indication of some of the ways that you can manipulate a data set, and along the way some geometrical things, random unit vectors, rotations, projections, eigenvectors, and eigenvalues.